Okay, good morning, almost good afternoon. Thank you for coming. This track is really focused on the architecture of Couchbase, so we'll have an introduction session, and then there are some others following. My name is Perry Krug. I'm an architect working in the office of our CTO. Wow, that's getting loud now. So I'll be moderating the first half of today, helping answer questions and all that. Without further ado, it is my pleasure to introduce our co-founder, longtime colleague of mine, Steve Yen, to take you through an overview, a whirlwind tour of the Couchbase server. So thank you very much.
All right, so you all can hear me okay? Okay, let's get started. So this talk is about the Couchbase server architecture. Hello, everybody. My name is Steve Yem. I'm one of the co-founders here at Couchbase. So I've been here since the beginning, and I've been always on the technical side, so on the engineering side of things. What we're going to talk about today is we're going to follow this algorithm of pretty much just zooming in into progressively more and more detail in the system. So starting with a cluster, double-clicking on that, coming down to a node, and looking inside what's going on inside the node or the main services. So a tour of all the main submodules of the system. So here we have a picture of a cluster. It's a cluster of Couchbase server nodes. And up on top here, you have applications, and these are using your Couchbase SDKs, using your favorite languages like Java and C#, Node.js, pick whatever you want. The nice thing about this layer of the application server is it's stateless. You can scale this out really easily as your business becomes more and more successful and you get more traffic. Just keep on adding more and more nodes. Sync Gateway, which is a product we have in order to integrate with mobile on the edge, works similarly. You could keep on adding more nodes. As far as the Couchbase server is concerned, Sync Gateway looks no different than any other kind of application SDK, right? So one of the things that might happen, of course, is like, bad things, right? So other companies have what they call the Chaos Monkey. We call this at Couchbase the Chaos Shark. So here the Chaos Shark has taken a bite out of one of your nodes, and well, what can happen? Well, because this is a nice stateless layer, it's really easy for your favorite monitoring system, pick whatever you want, Kubernetes, however you're going to be running your application server nodes, to come along and restart a particular node. That's all the nice part, but oops, what's happened here? Now the Couchbase Chaos Shark has come along and taken a bite out of one of these lower level Couchbase server nodes. So normally you have to do all sorts of things like, manually like rebalance or failover or those auto failover features, all sorts of stuff that can happen. But one of the things that we're proud to recently have announced is the Kubernetes Autonomous Operator for Couchbase. So that allows you to actually run your Couchbase nodes under the world of Kubernetes, which is like, I don't know, a year or two ago, that would have been an interesting thought because like Kubernetes is something that you use for stateless processing. But now, actually, how do you like manage all your persistent volumes and statefulness and sequence all the operations correctly? You could write it yourself. You could like script it up and work on all the steps that are needed in order to handle that. But we've done it already for you. So at 1:30 today, Anil and Mike have a talk about the Couchbase as a server using Kubernetes. Looking forward to that talk, where they're going to be talking about what are all the things that are available in this kind of world. So very cool thing. Let's drill into this Couchbase cluster for a bit. So if you were to double click on this colorful set of stuff, you'd see stuff like this. Now here the colors are starting to resolve into actually having text and labels on them. Each color represents a different feature or different service that we have in the system. So there's analytics, querying, indexing, full text, eventing, key value, and the cluster manager. Now, the base, most important thing with respect to the cluster is the lowest level thing here. So this dark gray cluster manager piece. You're going to need to have the cluster manager runs on every single node in the cluster Couchbase architecture. So what the cluster manager is doing is it's actually orchestrating or weaving together all the different nodes so that they form a cluster, so joining them together. The cluster manager must be running on every single node. But then the cluster manager is sort of like in charge of like spawning off and managing all the other child services that are there. For example, on this rightmost node here, it's running all the different services. So all the colors of the rainbow are enabled. But you can actually mix and match, and you can configure all the different nodes to run different subsets of the services. You could say, oh, I want 3 nodes to run this purple key value stuff, and I want 2 nodes to run the analytics. And so you could control actually how you actually want to dedicate the resources in your cluster to Couchbase. So that's one way of doing it. One popular way that we've seen people do this in production is, here I have a 8-node cluster, and again, they're all running the cluster manager service. Lots of people lay stuff out like this, where they say, okay, I'm going to dedicate one service to run on one node. So here I got 3 key value nodes, I got 2 analytics nodes, but it's like sort of one-to-one. That makes it easier to reason about what's going on, because you might say, well, you know, the key value stuff, I kind of want to be able to understand how much RAM, how much CPU, how much disk I/O I'm going to dedicate to that particular service. So this tends to be a good way of doing things. But there are trade-offs, right? Because now you're actually potentially using more nodes than you would have been before, where you can actually say, well, I actually want to have more than one thing running on one node. So stuff to think about. If you're to look at one particular node, and so we look at like these colors in the rainbow, let's go through them one by one and start with the lowest level thing. So if we were to double click on the cluster manager box and open that up, you know, inside of this dark gray box there would be more boxes. So the cluster manager, we consider this the control plane of the cluster. So major submodules that are in here, it's the thing that's powering up your administrative APIs and the user interface. So when you point your web browser at any particular Couchbase node at like port 8091, the thing that's serving that up, it's the cluster manager. So you can point your web browser at any particular node, because the cluster manager is running on every single node. The same UI is available across all the different nodes. It's also integrated with authentication and provides role-based access control. So that's RBAC, role-based access control. And one super important submodule is called the master services. What the master services are, it's sort of like the nodes, the various cluster managers are sort of electing well, a president or a leader. Like, so any node, any cluster manager can become the leader, but there's all this stuff that allows that election or that dedication of like who is going to be the master services node. What the master services node is doing is it's the thing that's orchestrating all the key cluster-wide operations. So rebalance and auto failover and failover, and also the automatic placement of shards or data partitions. These are all part of the core things that this master services or orchestrator is performing. So it's key to get that right. You know, if you have a presidential like, kind of service, you only want to make sure you only have one president at a time. So all that is very carefully attended to. The next thing are what we call the bucket services. So as you create buckets in Couchbase, which are basically containers for data, there is a clump of related subtasks that are related to managing and maintaining the information about that bucket. So if you create a bucket and you say, oh, I want replication count of like 1 or 2, well, there have to be all these replication streams that need to be configured and assigned and maintained and monitored. And so as you create more and more buckets, there are going to be more of these per bucket services that are created and monitored. So as part of those stat collections for bucket services, that's an important part. So collecting the stats for every bucket, collecting the stats and aggregating them all together, that's all part of like this subsystem. There are also per node services, so local heartbeats, and also a super important service we call the babysitter. So in some sense, we say that the babysitter, well, that's the thing that's in charge. It's actually the top of our process supervision tree. So if like a child is in trouble and it dies, the babysitter is the thing that's going to notice and restart the child. It's going to be the thing that realizes, oh, I've been restarting you like at a super high velocity. Let me go back off a little bit and give the system a chance to like heal a little bit, sort of like deal with all this kind of like process watchdog kind of responsibility. And then lower level, we have all these generic facilities, generic distributed facilities, generic local facilities. So there are things that, for example, well, there's all this configuration data that we need to take care of and gossip and send around to the various nodes. That's all handled by these lower level services. We kind of consider them generic because, in our opinion, you could build many different kinds of distributed systems, distributed clustered systems on top of these generic facilities. For example, there's a local configuration store, there's logging and log rotation. All these kind of things are not really Couchbase specific, but just nice things that are lower level services. So that's a quick tour of like what's going on in the cluster manager. Let's back out a bit and talk a little bit about automatic sharding. So I mentioned that the cluster manager or the master services within the cluster manager is responsible for like data partitioning and assigning basically the partitions to the various nodes. Well, how does that work? Here we have a diagram that shows like a 4-node cluster, node A, B, C, and D. And the cluster manager here is running on every single node and join these things all together into a cluster. The key value data service is running on every single node. And one of the things that is happening here is there is a concept of, for every bucket, a set of data partitions, or shards, or we call them V-buckets. Now, why do we call them V-buckets? It's sort of like lost to the history of time. But there are 1,024 V-buckets. And so they're all basically numbered from 0 to 1,023. And what the cluster manager does is it actually creates what's called a V-bucket map, or it's basically a shard map that tells you, like, for example, V-bucket 0, its primary node is going to be on node A. V-bucket 1 is on node B, V-bucket 2 is on node C, and so on, right? So this tells everybody, like, well, where's the data going to be? I see they're bringing in more chairs, so, like, you know, please help yourself to a seat if you can grab one. Let's keep on going. So one of the things that could happen here is your application on the top right there, it wants to, like, read data and mutate data. For example, it might want to update a user profile 1234. And it's going to talk to the SDK and use the APIs of the SDK. And what the SDK is going to do is it's going to run a hash algorithm, basically hash that key, user profile 1234, and it's going to generate a number. And that number is going to be taken as the vBucket ID or the shard ID. And then the SDK has a simple maneuver where it can just look up, oh, for example, vBucket 27. Which node owns vBucket 27? Oh, I see. According to this vBucket map, it's node C. And so the SDK can directly talk now to node C and say, hey, node C, for vBucket 27, can you get me, or I want to update the data associated with user profile 1234, and node C will say, yes, sir. I will let that operation proceed. So next, let's change things a little bit. Let's say we actually want to add a node. So going from a 4-node cluster from ABCD to a 5-node cluster, adding node E. So the first thing is cluster manager is going to, like, add that node and join it into the cluster and perform all the configuration, swapping and gossiping, and make sure everything's legit. But then it's going to start, like, arranging for vBuckets on the 4 old nodes, or a subset of the vBuckets to be reassigned to move over to the brand new node. And as part of that, a new vBucket map will be generated along the way. So in this case, vBucket 27, for example, has moved from node C to node E. So if the application comes along again and says, hey, I want to update user profile 1234, well, same algorithm, the SDK is going to take that key, it's going to hash it, it's going to get a vBucket ID, the same one as before because it's the same input. vBucket 27, it's going to look up, hey, well, which node owns vBucket 27? Oh, okay, I see it's node E, and it's going to talk directly to the node E and say, yes, node E, for vBucket 27, I would like to update user profile 1234, and node E is going to say, yes, sir, got that, I will let your operation proceed, right? But what if stuff happens, right? Like, let's say you have an application that's, like, relatively slow and didn't get the update of the latest and greatest vBucket map, because although the system is supposed to be broadcasting the vBucket map amongst all the different nodes and to all the different participants and to the SDKs, it's a distributed system. Like, some nodes might be, like, slow and behind the times. So if some application comes along and does this algorithm and gets vBucket 27, but it was using the old map, and it talks to node C, for example, node C should be able to say, oh, sir, you're asking for vBucket 27? I'm not the primary for vBucket 27, not my vBucket. In fact, the error code that you see encoded in the system is actually called not my vBucket. So when one of the SDKs or any of these people trying to run this algorithm get the not my vBucket error message, they can realize, oh, I need to go get a latest and greatest vBucket map because my old map, my current map, is out of date. Along the way, this has been optimized over the years so that, like, even on the error response of sending the not my vBucket message to the client, we already go ahead and send the latest and greatest vBucket map along with the error response. So all sorts of stuff like that is happening. So as part of this, there's, like, actually a very controlled takeover maneuver where ownership of vBucket 27, there's almost an invariant in the system which the cluster manager and there's all this, like, distributed state machine tries to make sure that vBucket 27 is only owned by a single node, at most a single node in the cluster at any time. So very important to understand. We talked a lot more about the happy path, like adding a node. But at 3:10, Dave Finlay is going to be talking about like what else could go wrong, right? What could possibly go wrong in like a distributed system, and how you can take your high availability to the next level. Really looking forward to this talk. Along the way, we talked about like for example, the V bucket moving from like node C to node E. Well, how does that actually happen? Well, underneath the hood, there is a protocol called DCP, or that's short for Database Change Protocol. So it's a protocol that we have developed over the years. It's high performance, does all this deduplication of mutations, it's ordered, it's restartable. And when you create a bucket, here I have a diagram showing 12 nodes, and like the key value data service is running on 3 of them. It's this database change protocol, or DCP, that's weaving them together. So when you actually say, hey, I want to create a bucket and I want replica count 1 or 2, it's the DCP data streams that are actually hooking the various nodes together and like sending information from primary node to replica nodes. But we actually use this DCP stream for many other things too. It's actually sort of like the backbone for all of our database changes. And you might have other services like analytics or indexing or full text or eventing. And they're all hooked up and they're all consumers of this DCP stream. And so that's how they get their updates. And we actually use it for a whole bunch of other stuff too, like other features like XDCR or cross data center replication. That's all powered by the DCP streams. Backup is also a consumer of the DCP stream. Sync gateway, same thing. And we also have third-party integrations, for example, to Hadoop and Kafka and other stuff, that same thing, powered by the DCP stream. So it's really a fundamental kind of backbone of how we actually deal with like our distributed changes. Okay, so we talked a bit about this a cluster manager. We've talked a bit about like how it deals with like automated shard placement and ownership of shards and the DCP protocol. Let's move up the stack a little bit and look at this next color on the rainbow. So the key value stuff, this purple stuff. If you were to double click into that purple box, you'd see more purple boxes. This key value data service, we consider this the data plane of the Couchbase cluster. So it's heritage-wise, it's based off the high-performance Memcached open source server. So basically, it's the core of our managed cache. So all that DNA in terms of like how networking is done, the networking I/O, and like the thread pooling and the handler threads for the different requests, and the lib event approach of asynchronous management of like processing, all coming from the high-performance Memcached code base. But along the way, we've added a whole bunch of stuff, like the whole data partitioning stuff that we've added, where we talked about V buckets. That's a concept that we've added over the years. There are sub-document operations so that you can actually say, I just don't want to, I want to do more than just gets and sets of entire values. I want to actually update like a subpart of a JSON document. So I don't actually want to like send the entire JSON document back and forth across the network in order to mutate things. Enterprise class authentication, LDAP integration, role-based access control, RBAC, all added over the years. And also, there's also, we've added like support for asynchronous task forkers and scheduling systems. And we use that for things like, for I/O, for when we need to actually persist dirty data down the disk, or retrieve data off of disk and put it back into the cache. We use it for things like expiring data and for cleanup of data structures, and to power up replication. So the way that like checkpoints are done in the DCP protocol, and the producer of the DCP protocol can send those checkpoints down a DCP data stream. That's all done for these like scheduled I/O background task maneuvers. Same with consuming a database change protocol. Okay, so that's a quick tour of the purple box. Let's like go back up. The next box I'd like to talk about is like a relatively new service, eventing. And this color is teal. If you were to click on that, you would get more teal colored boxes. Eventing is a consumer of the DCP stream that we talked about. And what is eventing? Eventing allows you to write JavaScript callbacks so that you can actually handle mutation events, like deletion events. And it powers up a nice web UI where you can actually, it eases your development of these JavaScript event callbacks. And you can actually set breakpoints, walk through your code, easily diagnose and debug what's going on with your callbacks. Pretty cool stuff. One cool thing that really makes it really easy is there's a JavaScript transpilation engine, or transpiler, that simplifies the way you can actually write your application logic. If you guys have seen classic JavaScript type maneuvers in the browser or in Node.js, you probably have seen it can easily become a spaghetti mess of like callbacks upon callbacks and nested callbacks. The transpiler allows you to actually deals with that in that it lets you write nice synchronous step-by-step logical code and does the work of like handling that stuff underneath the hood. In terms of APIs of what you can do when in an event handler, you can access data from your buckets, you can run nickel queries, you can call out the third-party services using REST or HTTP and other APIs. Underneath the hood, there's a pool of JavaScript workers that handle execution of these of your JavaScript callbacks. It's powered by the Google's V8 JavaScript engine, so it allows you to scale up to multi-cores and leverage all your CPUs. At 3.10, Siri is going to be able to talk a lot more about this and introduce eventing to you for those of you who are not familiar with it. Okay, so let's change this up a little bit. We've been kind of like building up from the bottom. Let's start from the top and pick up this color for analytics. I don't know what color this is, but if you double click on it, you get the same, a lot of boxes more of the same color. Again, this thing is a consumer of the DCP stream, showing how important DCP is. Some of you have seen the demo this morning. Know that this is part of our how we support like near real-time, like hybrid operational analytical processing. It's based off the DB open source project, and it supports Nickel for analytics, or basically it's a C++ dialect to allow you to do querying or ad hoc querying against JSON. So the nice thing about this is you can ask those questions, do all those analytical things without necessarily having to create upfront indexes. Now indexes will help, but you don't need to do anything if you just want to start playing around with it and using it. Now underneath the hood, it's based off there are basically sub-projects within the DB world. Like Apache Hyrax is what powers up this parallel runtime execution engine. Basically, you can provide this directed acyclic graph of operations and basically an execution program and say, hey, Hyrax, go execute this across multiple nodes. There's an advanced query optimizer called Algebrix. So all the stuff that Professor Mike Carey and team have built over the years, along with advanced parallel data flow operators. So the parallel distributed hash joins and stuff like that. Storage-wise, it uses LSM storage model, which is partitioned and optimized for high throughput across multiple disks. So if you actually have multiple disks mounted onto your one box, it can leverage all those spindles. It's designed for all that stuff. We actually have a separate track dedicated for introducing analytics to folks. So there's already an analytics talk happening right now, but there's another one later at 1:30, Nickel for analytics. Till is going to give a tutorial on that. Professor Mike Carey is going to do a drill down on what's going on underneath the hood of those subsystems, and that's at 3:10. Let's keep on going. So next thing is this red box for the query engine. So the query engine is basically the Nickel engine for the OLTP side of things. So it allows you to do the nested queries against heterogeneous data, and it lets you access all the distributed data that's partitioned across a cluster. And it's optimized for multi-core execution underneath the hood. What I mean by that is just drilling into that red box. If a client were to send a Nickel request, there's a whole bunch of steps that happen in order to process that particular Nickel request. You have to parse the Nickel query. There's a planning optimization phase that happens. Then a scanning phase that sets up basically scan cursors across all the indexes that need to be accessed. But then fetching and walking through those scanned cursors happens in parallel. Joining across all those different things happens in parallel. Filtering and pre-aggregate, again in parallel. The last aggregation step though is it's like a one-time thing, but sorting is in parallel, projection is in parallel. So basically, it lets you leverage, again, multiple cores. So there are multiple data streams happening through this data flow to leverage your multiple cores in a particular box. Next thing is this, the pink box, also known as global secondary indexes. So if you were to double-click on that, it's a subsystem that's pretty deeply integrated or with the Nickel query engine. For the OLTP side. One of the things that has been new here in 5.5 is this has picked up features for index partitioning and rebalance of those partitions. So you can actually have a nice thing here is like on a per index basis, you can actually specify different basic hashing policies. I want one index to be partitioned by zip code and another index to be partitioned by product category or something like that. Architecturally, one of the interesting sub-pieces about this is it actually has a submodule called the projector. Now the projector actually runs on every data node, so it runs close to the primary data. And what the projector can do is actually provide filtering and projection of the DCP stream. So you might be building up indexes, but in order to build up the index, you don't want to send all the data for the entire document across the pond, across the network. The projector actually filters out like just the fields that you're trying to index, and it can actually apply expressions to say like, oh, I just want the stuff that where like the employee salary is less than X, and only that subset of data is going to hit the indexing engine. When it does hit the indexing engine, there's a supervisor that is actually maintaining a whole bunch of state underneath the hood, including basically snapshots, so that you can get consistent scans from the core engine. And there are two different engines that are available. One is called Plasma, and one is called MOI, or Memory Optimized Index. Plasma is our latest generation storage engine for indexing, and it's actually, well, basically lock-free algorithms up the wazoo. So a lot of concurrent support underneath the hood. If you were to try and explain Plasma in a tweet, it's not a B tree. It's actually based off of what's called a BW tree algorithm. Instead of like the higher level nodes being like actually B tree nodes, it's actually we use a concurrent lock-free skip list. Now, the thing about the BW tree is like at the leaf nodes of each page in the leaf node data structure, there's actually a mini LSM approach. Basically, like pulling lock-free and going up and pulling it to the nines. There's another engine called the Memory Optimized Indexing Engine, or MOI. The difference of MOI is it's fully stored in memory, so your index must be completely in memory. So for certain use cases, that might be the right win. It does support asynchronous persistence, so that if a node like has some trouble, like you don't have to necessarily rebuild everything from zero all the time, but it's sort of meant for a different use case. And so the indexing engine, as the Nickel engine comes in and sends an index scan request, there's all sorts of optimizations to handle covered index scans and push down filtered snapshots of those index scans. 310, Keshav, who's sort of like head of all things Nickel and GSI, is going to be able to talk about the language and performance improvements that have been happening recently here. Okay, so we've gone sort of like bottoms up on the colors and top down on the colors, and then we've met in the middle. The last thing is this yellow full text box. If you were to double click on the full text yellow box, you'd see more yellow boxes. What's happening here is there's a REST web UI that lets you define basically full text index. It's integrated with authentication, so role-based access control is there. But it lets you specify full text indexes for one or many fields, or even entire documents or sub-documents. So dynamic indexing is supported. And also index partitioning is supported, along with optional replication. For each index partition, there's actually an instance of the Blevy open source full text engine that's running underneath the hood. So Blevy, for those of you who haven't heard of it, is very similar to Lucene, in that it's the thing that provides all this lexical analysis and stemming and stop words and all the things that you might expect in a full text search indexing system. For searches, it supports a whole menu of different kinds of searches, like wildcard searches, prefix searches, fuzzy searching, composite searches where you can put together different ands and ors and conjunction disjunctions, and it supports different data types, like not only just text, so you can actually also index numeric and Boolean types and geopoints too. So you could do searches like, oh, find me all the Japanese fusion restaurants that are within like a 5-mile radius of like, a certain geopoint. It also supports scoring and boosting so that for relevance, so that you could get the most important results earlier up on the search result page, and also sorting and faceting, which is also sort of like a runtime aggregation of results. So not only can you see like the first 10 results, but you could also get like a summary on the left that says, oh, like 20 of your results were like laptops, like 40 of your results were like PCs. 16 of your results were gaming PCs. Underneath the hood, there are multiple engines that are supported. The newest one is a recently introduced engine called Scorch. So that's where the latest and greatest like performance and optimizations have been happening. 1 o'clock, my colleague Abhinav and myself are going to actually be talking about full text search. So the title is actually not called The Secret of Full Text Search, but we're going to talk about the secret of full text search if you're interested in that. All right, so we've made it through the rainbow of colors. We've talked about the cluster manager. We've gone through, double-clicked in every one of these boxes and taken a look at what are the boxes under the boxes. If we had time, we'd go through another layer of like double-clicking on the double-click. So, but let's pull back out a little bit here. Zooming out. So again, the cluster manager is weaving these things together into a cluster. There are various indexing shards or data partitions that are like spread out across the various nodes. And that kind of like assignment of which node owns which shard is managed by the cluster manager. Those shards are owned by the key value system. The key value system has a replication stream so that like replicas across the key value nodes are maintained. And that's all driven from DCP streams. The DCP stream system is also used to like maintain the various other subsystems like the indexing and analytics and eventing and full text and other outside systems. A lot of these subsystems, when you actually do reads or actually want to access this data, a lot of them have like this, basically the scatter-gather kind of maneuvers that are hitting the various indexes or partitions as needed to like scatter a request across multiple nodes and pull things back together. Zooming out even more, you might have multiple clusters, and cross-data center replication or XDCR might be used to pull these things together. You might run this in all sorts of interesting topologies, multi-master, ring topology, star topology. Chaitra at 1:30 is going to be able to talk about like multi-region, active-active XDCR usage. Should be an interesting talk. And we've hit the end of like, trying to hit as much Couchbase architecture as we can. I want to thank you all for your time, but I'm going to be open for questions right after this. And I'll definitely be hanging out at the bar later, or the Connexpert bar. There's probably a microphone going to be passed around. Or
Cool. Thank you, Steve. Thank you very much. We'll take some questions now. I think we have about 15 minutes or so, so I'll try to walk around and get to you guys. Just raise your hands and be patient.
Thank you for the presentation. And a quick question on the near real-time data replication or on the analytics service standpoint. Can you elaborate a little bit what's a near real-time? Is like 5 seconds or 10 seconds or 1 hour?
So the question is like, what does near real-time mean? Well, it's not real-time. It's like it depends on what you mean by near too. So it's not like hours. It's like relatively fast, or at least it was designed to be that way. So it's all driven from DCP streams. So it depends on like. I'm reminded of like when you I don't know if you got like your architecture like 101 handbook when you became like a software engineer or architect. But on page 1 of the handbook, the classic answer is it depends. So well, it depends on like, well, how big is the node that is running the analytics system? How far behind is it? And like, what is the horsepower behind that thing? And yikes, so many interesting questions that could pop to mind. So sorry, it's like not a definitive answer, but it's probably what you expect.
Yeah, maybe I can provide some clarity. So it's, as Steve said, it's streaming from the data service, so memory to memory over DCP. So it's milliseconds to get from when you made the write over to where it's going to be processed. There's some amount of time to add that into the analytics service, and that depends on how much is coming through, but that's generally in milliseconds or low seconds as well. And then there's the query on top of it, and depending on how large of a request you're making, how complicated that query is, there's some amount of time in doing that. So it's, and that's in the hundreds of milliseconds to seconds, depending on what that is. So when we classify real time, we mean millisecond or below, right? And so that's your read or your write. That's your nickel query through the query engine is designed to be both high throughput and super low latency. The analytics side is not meant to be super high throughput, and it's not meant to be super low latency, but it's got to be as fast as possible, and you control that with kind of the hardware that you give to it. So not hours, not even minutes, but kind of seconds or milliseconds, depending on what you're trying to do. More questions? I'm sorry, I think you had a question first, and I'll come back to you.
Hi, question regarding consistency. So what I see, the architecture-wise, it's highly consistent for KV store. But when I go to nickel, it is inconsistent. If I just put an order from KV and I want to look at right away using some nickel query, I cannot see it. When are we going to solve that one problem?
So the question was about consistency, especially across the different services. So within like the KV world, things are, well, highly consistent or the most consistent because it's all within like a single process. But just physically there's basically a network hop going from the KV system to the indexing system. So by default, when you actually send in a query through like the SDK, there isn't, it's as free form as it can be. Like, you know, the indexing might be like behind, right? But if you want to, you can actually send in what we call this, like for example, at plus request consistency parameters, where you could say, no, I actually want to wait for the indexes to catch up. For example, the GSI indexes to catch up. But it gets really interesting because like now, while you're waiting for something to catch up, from a single thread or single client perspective, it looks all good. But the big thing is like, while you weren't looking, another concurrent client snuck in and messed around with your user profile or did something else. So eventually there becomes a challenge of like, you know, if you start putting in like a whole bunch of stuff to like, you know, correct for these kind of things, now you're slowing down everything. And now you're not going to be able to necessarily work at this like scale of like the massively interactive enterprise with like, you know, all your interactions. So it's like, that's like the fundamental trade-off that's there.
So just to add a bit of color, you're right that the key value, the data service, is strongly consistent out of the box by default. Where we kind of philosophically have turned things around is rather than being consistent on write for everything else, we are optionally consistent on read. And so if you take a traditional database or even some of the NoSQL technologies, when you make a write, it's going to hold that write until everything else is consistent with it. Indexes, multiple indexes, hundreds of indexes, and that implies and creates a slowdown on writes in order to maintain consistency, which might be what you want, but our philosophy has always been to get those writes into the system as quickly and as concurrently as possible. Where we allow for consistency is on read, when you make a query, when you make an FTS call, when you look at eventing, and now on a per read basis, you can say, I want this read to be consistent. I don't care about this one. I want it to be faster. The other kind of downstream benefit of that is for the reads that you are asking to be consistent, they only need to manage that path. So if I make a query that's using one of my 30 different indexes, and I say I want this query to be consistent, all it has to do is wait on that one index. The rest of the indexes aren't playing a role in that, and so they can continue keeping themselves updated, continue taking writes as quickly as possible, and any read to those other indexes is not going to be affected. So it does take a little bit of kind of shift of how you model it, but allows the system to work much faster for getting data in, as well as much more parallelly for all the requests that it's doing. Okay, and we're adding that to nickel. So it's just a matter of us allowing you to pass that parameter down. So it will be.
I have two geospatial use cases. One where I've got a bucket with a few 100,000 documents with latitudes and longitudes. Want to find all of the documents that are within a center point and radius of a given location. Is that something I would do through full text?
So the question is like, if you have like geo information inside your bucket,
Exactly.
Is that something that full text can do?
Yes.
Yes, it is. Along the way, so I'm going to refer to my handbook here.
Please do.
It depends. But yeah, full text can actually do.
Okay, and then a follow-up use case, I have another bucket with a few 100 million documents that are rapidly changing. I'm wondering if you'd still recommend full text as an approach, or if we should be using eventing or another system to offload that to another system that focuses on geospatial lookups.
The thing about eventing, I don't think it's, if you have like a bucket with a lot more documents and it's rapidly changing, could you use eventing for that? The thing about eventing is I don't think it comes out of the box with any geo spatial functions in it.
Right, we'd have to use
have
it to
to-
offload the data to someplace else.
Yeah, so then.
I guess the
depends.
question
Do you have
is-
a place to offload the data? But
Can-
full text ought to do the
Can,
trick.
can
too.
full text keep up with that kind of mutation rate? I think that's the question.
Yes, I think so.
Okay.
But I might have a image in my head of like keeping up,
Perfect.
and you might have a different.
Okay. Well, if we can get a couple of minutes, I'll give you a little
Yeah.
closer to what our
Oh,
image
yeah,
looks like.
would love to hear it.
Thank you.
Yeah.
A question on the DCP.
Yeah.
Are we going to get all the mutations for the historical data on the document?
Question on the DCP, are you going to get all the historical data or mutations on the
Yes.
document? Quick answer is no, but let me explain. DCP, as part of like the key value system, actually, in order to get it to perform, there's actually a deduplication step. So if you're like, if your application is like rapidly updating like this, spamming on this one key, not necessarily all the mutation history against that key are going to make it outside of the purple box.
The reason why, we wanted to do the auditing on this document.
Yep.
So, is there any roadmap to implement that?
Is there any roadmap to implement it? Well, I do see some product managers in the room, but one of the trade-offs there would be the deduplication is a performance win. It's a terrific win. So now, if you want all the history, now you have it's a trade-off, right? So now, one thing that we've seen users do is sometimes they manage it themselves, where you can imagine a document with its like change history, and it depends on like the kind of data that you have, or they split out their change history into separate documents, and they carefully architect their application so that they are doing this append-only kind of maneuver against their logical model. So that's one way that application folks can take control into their own hands.
Okay. Thank
Good
you.
question. Yeah.
Cool. We've got about 5 minutes left. Question up front, and I'll come back to you, Bob.
For the key value store,
Yeah.
if the value is too large, how do you handle that?
If the value is too large, well, it depends on too large, but yes, eventually it will be too large and we'll return an error and say, that's too big. So like it's like 20 megabytes?
20
If I last
megabytes.
remember.
And so if you send something over 20 megabytes,
Yeah.
you'll get a quick error back says it's too large.
Yeah, so if one of the philosophies is like don't store video in Couchbase, store like the pointer to the video in Couchbase. Right? Is there sharding on the value? No, there's no, that 20 megabyte limit up to that is like considered a big blob. It could be a giant JSON thing, but it's like a blob.
Just a question about the DCP protocol. So if a server, one of the receivers goes down for a period of time, right, DCP has to be able to buffer and help it catch up when it recovers. How do you deal with, how much retention is there if you have like a prolonged outage of one of your analytic or event nodes? And in general, how does it deal with the possibility of a server that can't keep up, right? If you find that you've undersized your indexing nodes or something in a larger deployment.
Yep. So the question is like, well, the first one is like, what happens if, I guess, if a consumer is really slow, and is there buffering, and like, how does that actually work? There is buffering. There is a concept that we have called checkpoints, or also called snapshots, that are actually persisted down. So there is like a window of time, and it's escaping me actually how long that is, but where like a consumer that disconnects and reconnects, as long as it's within that window of time, it could pick up where it left off. Eventually, though, physics, you're gonna imagine it's gonna not have enough buffer, and on the next reconnect, the client is gonna say, hey, I need to start from this sequence number at this snapshot, and the server's gonna say, ooh, shoot, I don't got that for you anymore. Can you? I guess you have to go back all the way to 0 potentially, right? So you have to reinitialize from the latest snapshot, essentially. Yeah. So the consumer remembers like where it was at, and it uses that to negotiate when it reconnects to say, hey, I'd like to restart where I think I left off, and the server says yes or no. Sorry, I guess there was a second question there, or that was part? Okay.
So for the eventing, you can have HTTP like endpoint, right? So if it's like endpoint is very slow, how how is that is going to be, I mean, buffering on the event server side, or how it's being handled?
So if you, I guess in the eventing, there's an API in order to access third-party endpoints. If the endpoint is really slow, well, be careful, because you could potentially cause all this back pressure that makes the venting slow, and then then you run into the problem where the venting isn't keeping up, right? But I don't know offhand if there's a timeout on this. Actually, Venkat might know.
So actually, our eventing expert is. You want to answer this one, or you want me to? And it's also kind of multi-threaded and parallelized. So that one call is slow. Other nodes are able to keep processing their functions. But yes, in general, you want to keep that flowing quickly, and that's where timeouts come in, and making sure that whatever's on the other side is able to keep up with that.
But you don't lose track of the mutation. You will not lose the mutation as such. Essentially, the rest of the things in the backlog will continue to be processed as it comes. As this event alone times out, the rest of the mutations in the backlog will be processed.
Okay. We got maybe time for two more.
So I had a question around rebalancing. Do you have any rebalancing strategies if I have a 2 billion keys or something that I want to rebalance when I add nodes or when I remove nodes? Does it impact the end user, end client, or the client app?
So the question is do we have? I guess it's a rebalance related question. If we have, do we do anything different if they're depending on the number of items?
High volume, high traffic happening, and I add a node. Does that impact anything on the
and also does it impact, for example, operations per second or existing performance when you add a node? Well, it was designed not to, but all that depends. Is your system properly sized? Is there enough resource headroom? So that we've seen customers run these things right up to the edge, and then they want to hit rebalance button, and it's ooh, yeah, you should actually have some headroom there,
It's designed to, and there are things in there that are intelligent enough to do that. As Steve said, you can get it to a point where you will see an impact. We've actually got a kind of a work stream going on right now for next year that's going to add a lot of improvements around that. For right now, the vast majority of our applications run without any impact. A small majority know that they will have some impact, and so decide to do it kind of at off hours or off times. Our focus is always on availability. So throughout the whole rebalance process, the application is available, and then performance is going to depend a little bit on your resources and how close to that edge you are.
But just while you're walking over there, I see the one more. I don't think of in the code itself there's actually anything that does anything different. But if greater than 1 billion, then do something else. There's nothing. It's kind of sort of the same algorithm that's driving it all.
At a data size, yes, but there are other kind of throttles that kick in regardless of how much data you have.
Right. For example, on the DCP thing, there's back pressure on the system that says hey, or I got a slow consumer, I need to back off on not kill the stream with stuff that you're not going to be able to process fast enough. All sorts of things that have been baked in over the years into this.
Yeah, and
okay.
We found IOPS become a real issue here. Sometimes you don't watch that until you get to really high volumes, and then you realize you got a pressure you didn't expect on. So you definitely need to make sure you've got the bandwidth to support the rebalance.
Yep.
Okay, one more question, and then we'll let you go.
It's on the same lines. So if we have high volume of data and we are rebalancing, is there a way to throttle the rebalance so that it does not impact the memory if in case?
Is there a way of throttling rebalance so it doesn't impact? This is where we're getting to undocumented, under-tested knobs, but the key thing is undocumented, underdocumented. Generally, I would then, because it's underdocumented, say no, we don't.
Yeah, at the moment, we don't have kind of exposed tools for you to turn that knob. There's some stuff that our kind of support team can advise in the specific cases, and it's also something we're continuing to work on optimizing. It's gotten much better over the last 8 years or so, and our approach is to try to do as much kind of dynamically and automatically for you, so that you don't shoot yourself in the foot. But we do have a gun to hand to you.
But it's also like philosophically sort of I guess a priority in the designers' heads that we're thinking like, if they want to rebalance, they probably want to get it over with as fast as they can. But it looks like you have another, it depends answer. I want to thank everybody for your time here. This is thank you for coming to this talk.
Thank you, Steve.